Uh, in the previous lecture, I was telling you that the wavelength determines the level of resolution. If the wavelength is shorter, then you will be able to resolve smaller things. If the wavelength is longer, then you will not be able to resolve smaller features, right? So if you have, for example, a 1 meter stick, you cannot measure with it 2 centimeter or 3 centimeter thing, which is not visible. I'm just giving you the example. On a 1 meter stick or meter rod, you have labels. It is 1 centimeter, 2 centimeter, or 3 centimeter. But when you can't see them, the features are very, very fine. Then scientifically, you can go up to half the wavelength of the radiation you are using. So if the wavelength of the radiation is 1 micron, 1 micrometer, then you can resolve features up to half a micron. But if it is below that, then you can't do it with this equation. So the resolving power or the resolution, you can say, is determined by 0.61 into lambda of the relevant radiation you are using divided by the numerical aperture. Now lambda is the wavelength, and in the case of visible light, it is 0.55 micrometer. So when you put that value for a numerical aperture 0.9, then you will be able to resolve feature up to down to 0.37 micrometer. But as it is commonly observed in science that theory tells you something else, but experiment has many other flaws associated with it. So that the things which you derive to theory are not usually accessible experimentally. So if you have 0.37 micrometer, it is excellent, but it is not possible because the instrumental errors and all the things are coming down there. In the X-ray, you commonly see that if you have an XRD pattern of a material, then when you see the interplanar spacing is 3.37, then it should be a point here, a line here, 3.37, but it should be like this. But what you get a peak like this. So it starts from here and comes down here. Instead of this single line, you are getting a peak, and that is the instrumental error, which gives you a broader peak instead of a single line. If it is 3.37, then 3.37 is one value. It is not 3.36 to 3.38, right? And these things come because of the instrumental errors. For example, you pass current in a conductor and you connect it with a source which is, for example, 1 ampere, but at the other end you are not getting 1 ampere. Resistance up to some level reduces it. The same thing is here. The interplanar spacings which are struck by the X-rays or electron beams or other diffracting radiations, the information from there comes exactly 3.37. but it is the electronics which transforms the material into that output. It is not the same. So if you see 0.37, then it will come in the forward coming lectures, but I'm just telling you that if I get 0.37 angstrom and that resolution is achieved with a 100 kV electron microscope, but in practice it is not that. So you allow some space, some room for the electronics associated with the detection and transformation of the outgoing radiations, which are converted, for example, from analog to digital conversion, from digital to analog conversion. And this conversion, a lot of information is a little bit moved around, and that is why you don't get the specific resolution which is expected from a specific. Again, I am reminding you that gamma rays range from that about 10 power minus 2 nanometer. 10 power minus 2 nanometer is 1 nanometer over 100. So it is 1 nanometer over 100. 10 angstrom over 100. 10 angstrom over 100 means 0.1. Right? So clarify these things in your mind, because science, physics are all associated with measurements. If something cannot be measured accurately, then it is not science. Right? If I tell you that a flower is beautiful, you say that I have seen a flower more beautiful than this. Another person say, no, it is not beautiful. That particular flower is more beautiful. So what does this mean? This means that the beauty is not measurable. So it is not science. If you say something is 1 kg, then everybody can measure it. And at every corner of the earth, it will be 1 kg. So 2 points are very, very important. I usually used to tell some jokes with the students that we have a cat in our house. We have a cat in our house, but it sleeps with chickens and it started eggs. It lays eggs. Will you believe it? It can be a miracle, but it is not science. Science, 2 things, measurability, and the second is reproducibility. If something is not reproducible, it is not science. If something is not measurable, it is not science. Therefore, you must be very careful that whatever you do, you must give the accurate units and the accurate numbers as much as you can. There are usually errors. And when you submit a research manuscript to a journal for publication, and the reviewer is a standard, knowledgeable person, then the first thing that he or she will ask that what were the errors. So if you don't have plus minus 1, plus minus 2, plus minus 3, plus minus 0.001, right? But the error must be there. And error arises from statistics. That if you do so many experiments where a good statistic calculation can be made, then the error is derived from there. Standard deviation or any sort of statistic cannot be done with a single measurement. There must be several measurements which are statistically feasible to be estimated that what sort of error is there. So science people always stress upon the repetition, and if there is error in the measurement, it must be clearly given. For example, in the world, people are working on soft magnetic alloys. I myself worked on that. That is why I am giving you that example. One day, my supervisor asked me that how much is the coercivity of this material. I said, sir, it is about zero point 0.5 amperes per meter, right? Zero point 0.5 amperes per meter, for example. He told me that the world record is zero point 0.4 or something like that. Can't you decrease it a little bit so that we reach the world record? I told him that yes, I'll make it zero point 0.2 if you like, but that will not be correct. And he asked me why. I told him that the error in the machine is zero point 0.2 or zero point 0.1. So if the error is zero point 0.1, then I can't call 3 as 3, but it is zero point 0.3 plus minus zero point 0.1. So zero point 0.3 plus minus zero point 0.1 means zero point 0.4 and zero point 0.2 and zero point 0.3 and any value in between them. So always be careful that if you give accuracy about something, do you have the facility to accurately measure things up to that level? If you don't have that facility, then you are lying. And lying is the worst crime, worst sort of crime in science. People know, the people who know, they know what they are reading and what they are assessing, right? So, from point 1, 10 angstrom over 100 means 1 angstrom over 10, so zero point 0.1 angstrom up to 10 power minus 6 means divided by 10, so it will be, multiply it by 10, so it will be 10 power minus 5 angstroms. 10 power minus 5 angstroms. So the range of gamma rays is from 0.1 to 10 power minus 5. 10 power minus 5 means 1 over 10,000? Yes. 100,000. 100,000, right? Angstrom. Then X-rays range, I told you time and again that it ranges from slightly above 10 nanometer. Slightly above 10 nanometer means about 8 nanometers, which is 80 angstrom. And on the top side, it is below 0.1 angstrom. So below 0.1 angstrom will be 0.2, 0.3 are like that. So when you start from 0.3 angstrom up to 80 angstrom, most of the crystallographic latest parameters are covered in that range. The commonly used X-rays are copper. They use the copper source for X-ray, and its wavelength is, the wavelength of copper is 1.54 something something up to several decimal points. 1.54. So 1.54 radiation, the radiation with a wavelength of 1.54 will give you resolution theoretically of 0.7 something angstrom. And 0.7 something angstrom will be a little bit higher than that due to the instrumental errors and things like that. So let us say it is 1. Then from 1 angstrom up to 80 angstrom, the whole area is covered. You can pick, you can diffract, you can play with the planes and the latest parameters in that range. And that is why X-ray is the most popular technique for determination of latest parameters, interplanar spacings, bending within the planes. When you talk about the defects in crystals and stresses in crystal, then if there is a stress in the plane, then the diffraction from that plane will be different from the one which is not under stress. The stress will a little bit widen the gap between planes, or it will shrink. When one region is under stress, then the other region will be under strain automatically. And that will give you variation in the interplanar spacings. And you will be able to measure the stresses inside a material. Similarly, people usually say that with Scherer formula, uh, you can measure the grain size. It is not grain size. Grain may contain many crystals. It is the crystallite size, right? So never say grain size. Grain is not a crystal. And X-ray deals with crystals. It is not dealing with grains, right? So it is the crystallite size which the Scherer formula gives you, right? And that is again you full width of the half maximum of the peak, and then it is put in the Scherer formula and you calculate the crystallite size inside the material. Now, if you do XRD of a material and you calculate the crystallite size using the Scherer formula, and then you do transmission electron microscopy and look into the crystal size and they are not matching, then what will you do?